So that's a very good question. One of the problems with New Zealand is it's tiny, its population is tiny, and the population of structural engineers is even smaller. Why would any decent software engineering company produce software for such a tiny audience? And you found out they haven't. So New Zealand has a dearth of software. And I hate to tell you this, but the vast majority of calculations in New Zealand are done by hand, pencil and paper. The intrusion of computers is a relatively new thing. And a lot of engineers think that they're pretty advanced because they use Excel. Yeah. Now, you can do an awful lot of things in Excel, but if you want a little bit of fun, do a Google search for Excel is evil. And it'll tell you, don't do it on Microsoft because it gets angry. Because I typed in Excel is evil in the Microsoft browser and it replied, I'm sorry to hear that. Worrying. But other browsers will bring you to a whole series of websites and YouTube channels, which people have criticized Excel. It's not so much the critical use of Excel, it's how people are using it. Don't forget, Excel is a spreadsheet tool, and it was made for counting lists of numbers. And that's really what it's good at. It's really good at counting numbers, adding up lists and lists and lists. It's really aimed at accountants. It's never aimed at engineers, but engineers picked up on it. And it's said to be the killer application for personal computers. And so as soon as spreadsheets came out, Excel wasn't the first, there were others. SuperCalc and Lotus 123. And we thought this was amazing because we could first of all do load takes for the whole building to get our foundation loads. And it's basically multiplying your areas by the loads, add on a load factor, hey presto, magically you've got the number. You didn't have to work it out by hand. And then little by little by little, they've added more to it, or engineers have added more to it and asked it to do a lot more. There is a programming language behind it, the Visual Basic basically behind the Microsoft products, and you can run macros, and your macros can do amazing things with the data in it. And you'll come across, if you start working for an engineering company in New Zealand, they will present you with a load of spreadsheets. This is how we do our work. This is how we do design. Not really. These are tools. Excel is a tool, and it's a good way of presenting information. It's a much neater way of presenting information that you don't have to reproduce again and again. Here is a template, pop in the numbers, and out pops the answer in the other end. And it's really good for beams, rafters, purlins, standard things that you're going to do day in, day out. What you should say is, first of all, where did this come from? Who's written it and who's validated it and how's it been validated? If the answer is, I don't know, nobody knows, it's lost in the distance, because chances are the person who wrote the software, who wrote their Excel spreadsheet has left, and they took their knowledge and their assumptions with them. So every piece of software and every Excel spreadsheet will have a whole load of assumptions made. And people will take that and use it to do something else, way beyond the original scope. So yes, you can dumbly use Excel. And as I said, and we do it in Redco. What we do is we get a graduate and plot them in front of a computer and give them a load of Excel sheets. And here's a steel framed house, design that lintel, it's great. Put the numbers in, hey presto, you get the answer. The engineer has got no idea how that works. So they should ask, where's it come from? And you probably get a lot of annoyance from your senior engineer. But it's important for you to understand it. Do you want to be an engineer or do you want to be a spreadsheet jockey? So basically, if you're going to just punch in spreadsheets, you can take somebody who's 16 from school and do that. You do not need a degree in engineering. You've wasted your time if that's all you're going to do. And I've got this persistent campaign that engineers don't want to be spreadsheet jockeys, that they need to understand what's going on behind the spreadsheet. So Mathcad is a really good way of checking your Excel sheet. You have to know what, well, you have to have a Mathcad anyway, but it's a good way of checking what's going on in the Excel sheet, because everybody hides their working out. And so when you're presented with this as a checking engineer, you go, well, where's this come from? The other thing, Excel is no good at units. And there are many cases where the units have gone wrong. And it's a unit conversion problem. And when you're going, you're getting your stresses out in MPa, but you put something in kilonewtons, there's a lot of factors to change. It gets even worse if you're dealing with the conversion from imperial units to metric units. So one of the main advantages of Mathcad is it's very good at units, and it does dimensional checking, and it won't let you get away with the sloppiness that the standards are using. And when you use Mathcad, you realize that many of the equations that are given in the standard are actually unit dependent, but they don't tell you that. Not only are they unit dependent, they're a particular unit dependent on it, so they don't tell you what those are. So yes, I wouldn't expect you to use Mathcad every time. So the argument is that if a new engineer comes in and they're given a spreadsheet, they need to do that calculation by hand. And so that's the next question you ask to your senior engineer is, where is your validation calculation for this? Oh, well, it's somewhere. Trust me, I'm an engineer, yeah. But to satisfy yourself, and it's doubly worse for 600 because it's all about buckling and stress and so on. And the software available for light gauge steel is, well, pretty much non-existent. We've got that thing from Sydney University, which is quite handy, but it's always worth checking. And in part B, we'll get on to connections. There's no software for connections in light gauge steel. There are tables, some are right, some are wrong, some are useful, some are not. So we'll get on to that. Okay, that was an interesting pause. So in brief, I've showed you the working out in the software. So typically, if you've got a frame to analyze, you would probably do it eventually. You'd probably eventually do it in a piece of software like multi-frame or space gas or something else. And if your boss has paid for the extras to do the design, then you can often do the design in that software. But quite often you'll end up stuck and you've got no idea why you're stuck. The software is telling you it doesn't work. And then you've got no idea why it doesn't work. It's probably not working because you haven't put in the correct restraints. You've assumed your portal frame is unrestrained all its length and it's flopping over. Well, it would do. Or even worse, it's working and you don't know why it's worked. And it's worked because you've restrained everything. You've assumed this portal frame is restrained all the way along, and it's, you know, not subject to out of plane buckling. That's possibly worse. Or another favourite is you've got this possibility of ignoring tension-only members. Now you'll see the bracing is often done either with cables or bars or straps. And like a rope, you can pull on a rope, you can pull on a strap, you can pull on a cable. Try squashing it. It just moves out of the way. But in your piece of software, you can click that checkbox and you'll be able to push on a rope. And suddenly your frame is very stiff and it doesn't move at all. And you think this is brilliant. And you go, no. So the other thing you need to get awareness of is you've got to be able to look at computer output and go, crap. You've got to have a crap detector, because your engineer will spit out thousands of pages of calculations, thousands of pages of numbers, which mean nothing. And they say, my frame works, my building works, it's all good. The trouble is their assumptions are wrong. And if your assumptions are wrong, the building's wrong and the building falls down. Yeah, so, and again, when you're developing, you won't necessarily start with a three-dimensional frame analysis. You will start possibly with a two-dimensional analysis. You could start with a hand analysis. So to get the rough order of magnitude of the moments on your frame, you can do a Klein logo. And so you can do that by hand. Or if you're smart, you do it by Mathcad. And in one page, you'll see, right, that's the moment on it. And that's a sort of section size I need for that, that loading.